Hello, we are Team Interrobang and I'm Hin Bong. And in this video, I will try to convince you why you need threads in your OS. So here we have a single-threaded process and a multi-threaded process. In a multi-threaded process, all threads share the same code, data, and files, but they each must have their own program counter, register, and stack. Why would you want threads in the first place? Well, let's say your word processor is a process, but it has multiple threads controlling its save state, your keystrokes, and your spelling. If you didn't have a thread to control your save state, if there's a power outage, you would lose all your data, which would suck. This is a diagram of a multi-core programming. So let's say you have a multi-threaded process running on a single core. That will be very slow and inefficient because each thread will have to wait for the other to finish. Whereas if you had multiple cores, you could initiate true parallelism, which is basically putting different threads on different cores to allow for faster execution. The challenges of programming threads on a multi-core system is you have to find tasks inside your process that needs threads. You want to provide each thread a good task to perform. You want to waste threads on trivial tasks. You want to make sure that each thread does not interfere with another. And just like math, you want to make sure that if you have threads that depend on one another, you want to make sure that you do your addition and multiplication before you subtract and add, just like PEM does. There are two types of parallelism. There's data parallelism, which is if you have a 10,000 piece puzzle and you have 5 friends, each friend is a thread trying to figure out where each puzzle piece goes. It's basically doing a small part of something big. And task parallelism is basically assigning each thread an independent task they can perform. Before I talk about multi-threading models, you need to understand that there are user threads and kernel threads. User threads must be mapped onto kernel threads because kernel threads are where you can execute all your tasks and do system calls. So this is the many-to-many implementation of a multi-threaded model. You want this because if one thread has to block, the whole process will not cancel because you have multiple kernels the other threads can go to. And each kernel represents how many cores you can use. So let's say in this diagram you see 3 kernels. That means there are 3 cores that you can map each kernel onto. And it's just super efficient. So this is code for how to implement threads using a runnable interface. Java lets you either extend a class or implement a runnable interface to create a thread. I'm showing you how to do the implementation. So when you implement runnable interface, you need to implement a run method because that run method is one thread, whereas your main method is basically another thread. And in this program, you see that you need, in the bottom right here, you see that you need to create an object of my runnable thread and you need to create a thread object. Once you put your runnable thread object into the constructor of your thread, then you need to call t.start, which is basically thread.start, because threads need to be started before they can run. And when you do that, this program basically, once your main thread will increment a global variable, it'll sleep, the other thread will increment that variable, it'll sleep, and it'll go back and forth until it ends. The output will look like this. It'll go from 1 to 10. It's basically 2 threads incrementing the same variable. This is basically the same thing, but you are using threads to sum up integers, user-specified integers. Thank you, and we will move on to scheduling now. And the takeaway from this is that you want threads because they help multiple tasks be performed at the same time. And that's fast. And you want fast, like the Flash. Thank you.
I'm David Chow of Team Interrobang, and I will convince you why scheduling is important to an operating system. In a single processor system, only one process may run while others must wait until the CPU is freed and can be rescheduled. What if that process runs, but then it comes to a wait state, waiting for an IO request to be done? The CPU must then be idle, wasting time since the CPU could be doing something else while waiting for the request to finish. In a multi-programming OS, the OS takes the CPU away from the waiting process and gives that CPU to another process, rinse and repeat. As you can see, scheduling is a linchpin to the OS, because without it, the CPU would waste resources doing nothing. What are the different scheduling algorithms? Well, there are various scheduling algorithms that deal with the problem of deciding which of the processes in the ready queue is to be allocated the CPU, such as the first come first serve, simplest to implement since the first task to come is the first to leave. Average waiting time is long, however. This algorithm is non-preemptive. Once the CPU is allocated, it stays allocated, not getting stolen by another process. Round robin. Preemptive algorithm where each process gets only a time slice before the CPU is allocated to another process in a circular queue. Short stop first. Best approach to minimize average waiting time. Processes with short CPU bursts have higher priority. Hard to implement, however, because there's no way of knowing the length of the next CPU burst. We can, however, predict it through various calculations. Priority scheduling. A general form of SJF where each process has a priority associated with it. Starvation may occur when lower priority processes are added to the queue and there is a large amount of higher priority processes being run. Here's a pseudocode from our OS which shows the round robin algorithm. Here you can see that the scheduler gives each process only a second or so to run its I/O operations before being preempted by the next process in the queue. The reason why we implemented round robin rather than any other scheduling algorithms is because it is similar to first come first serve implementation wise, while being efficient as we kept the time slice to about a second. There are many ways to choose which scheduling algorithm your OS needs, based on various criteria. CPU utilization, keeping the CPU as busy as possible. Throughput, the rate of time the CPU is doing work, measured in processes per time unit. Turnaround time, how long it takes to execute a process from start to finish. Waiting time, the sum of the length of the waiting period of a process while in the ready queue. Response time, the time from the submission of a request till the response is produced, not the output of a response. Obviously, we'd want to maximize CPU utilization and throughput, and to minimize turnaround time, waiting time, and response time. In most cases, we optimize the average measure. Sometimes we may optimize the minimum or maximum rather than the average. For example, to have all users get good service, we'd minimize response time. Once you pick your various criteria, you may want to do some calculations or try simulations to test whether the scheduling algorithm meets your criteria. However, the only completely accurate way to evaluate a scheduling algorithm is to code it, put in the OS, and see how it works. This approach puts the actual algorithm and the real system for evaluation under real operating conditions.
Hello, my name is Andrew Goff of Team Interrobang, and I'm going to try to convince you to include some form of memory management in your operating system. Now, your OS more than likely needs memory management because without it, you're likely to run into CPU stalls. A CPU stall occurs when your CPU lacks the information to finish an instruction and has to waste precious CPU cycles retrieving or storing information to your main memory. One way to reduce this time is to add a store of memory to the CPU chip called a cache, but this can be expensive, so other methods must be used. One such method is swapping, which is relatively simple. By keeping as many processes in memory as possible, less memory accesses are required, which results in less CPU stalls. We can have more processes in memory by swapping processes that aren't in use with new processes, and then swapping those new processes back out when we need to use the old processes. With swapping, we can make it seem as if more processes are in memory than physically possible, but doing so requires a fast form of memory to move the process to. Another way to keep as many processes in memory as possible is to properly allocate your processes so that little memory is wasted. The easiest way to do this is to allocate your memory contiguously. This can be done by using a table that keeps track of what memory is available for use and what parts are occupied. When a process is loaded into memory, the table is checked for available memory and the process is loaded if possible. When the process is no longer needed, the process is unloaded from memory. The process of loading and unloading ends up leaving holes in memory referred to as fragmentation. Fragmentation is a problem since we're trying to conserve as much memory as possible. We can help reduce fragmentation, though, through the use of segmentation. By organizing portions of a process into segments, the address space of the process is no longer contiguous. This can be done by splitting up a process's code into different segments, such as the stack, the main program, the symbol table, the subroutine, and the square root method shown as in the diagram. Since the process is no longer contiguous, parts of the process can be stored in smaller areas, reducing fragmentation. Paging works similarly to segmentation in that it allows processes to be stored non-contiguously. Rather than breaking a process into segments based upon its code, paging organizes physical memory into same-sized blocks called frames, and logical memory into same-sized blocks called pages. When a process is loaded, its pages are stored into available frames, and when the process is unloaded, those frames are freed up. Fragmentation is reduced externally since each frame can hold one page no matter what, but internal fragmentation might be a problem. As an example, if a page size is 32 bytes and a process takes up 33 bytes, then 2 pages must be allocated for the process, resulting in 31 bytes being lost to fragmentation. Reducing page size can help reduce internal fragmentation, but at the cost of the time it takes to add each page table entry. And while coding all of this would be extremely difficult, because a lot of it also requires some hardware to do, here is a simple C code for Linux that will get your page size and return it to the console.
Hi everyone, I'm going to go over a little bit about storage and why it's needed within an operating system. I'm also going to go over about how we actually implemented storage within our own operating system. Since main memory is usually too small to accommodate all the data and programs permanently, the computer system must provide a secondary storage to back up main memory. Modern computer systems use physical drives as the primary storage medium for information. These physical storage drives have come a long way since the first computer tape drive from 1951. As you can see in the picture, hard disks were much bigger than they are today. They were also much more expensive. All the way up into the 1980s, hard disks were only included as expensive add-ons for computers. Today, we have flash drives and solid-state drives which are much smaller and portable. With the invention of cloud storage, which allows users to access data directly from remote servers through the internet, we theoretically can have an unlimited amount of storage on any operating system. It is also very common today to see any computer come up with some sort of storage device to ensure a working and efficient operating system. Storage devices may be partitioned by dividing up the physical memory from the storage device. Typically, booting an operating system requires having some sort of physical storage to access a boot partition. The boot partition plays an important role in ensuring that the correct operating system boots up, since the boot partition contains the actual operating system as well as all the device drivers used by the firmware at runtime. Partitions also allow for multiple operating systems to be ran on the same physical storage device by formatting different partitions with the respective file system and boot partitions. As you can see in the picture, here is a physical storage device which is split up into separate partitions. The device contains 3 boot partitions, one for each respective operating system. A file is basically a collection of related information defined on creation. These files are mapped by the operating system onto physical devices. For our operating system, we used IndexedDB to store our files. IndexedDB is a transactional database that is embedded within the browser. IndexedDB stores the data right on your physical hard drive by creating local JSON object collections that IndexedDB then can store or retrieve information from locally. This means that anyone using our operating system can create or remove files and still have these changes modified after they reload our operating system's webpage. Looking at some simple IndexedDB pseudocode, we can see how easy it is to store new files within our operating system. We first create an object store in the database and we name it directory to keep things simple. We then create indices of the collection of information each file contains in our operating system. This information includes the path, name, and content of each file. We could then simply add new files to this directory by supplying information about the path, name, and content of each file. We can also easily read from the database by first opening up a connection to the database. We then create a transaction to the directory we want to access, and lastly, we can retrieve the file by searching the file name index by providing the file name that is stored within the database. All files stored within our operating system use the same scheme to store and retrieve file information.
Hello there, my name is Hao, and the topic for today's presentation is file systems of an operating system. Just like how physical documents and files has a file system in place to keep documents organized. Each operating system would have their own individual file systems to keep their own files organized. In order to organize files, each file of an operating system should have a base set of attributes that identifies each individual file, allowing for easy organization. The set of attributes should include the name of the file for the user to identify the file, an identifier for the file for the operating system to identify the file, the type of the file telling the operating system whether the type is supported or not, the current location of the file, and access control to the file, limiting the amount of users being able to modify the file. Now let's look at a Linux file system. The Linux file system has a tree-like structure, also known as the directory tree. In a Linux file system, each directory has a parent directory, with the exception of / representing the root directory. The root directory is the only directory in the tree without a parent directory. Now, in order to traverse the tree, we start from the root, which contains files and subdirectories, which in turn contains more files and subdirectories, and so on. Navigating from the root, we are able to traverse the tree. Right after the root directory, there is the bin directory, which holds all executable binary programs. The dev directory holds all files for the hardware's devices on the machine. The op directory holds all third-party applications, for example, Google Chrome or Java. The user directory is the largest directory of all, which contains all executable binaries, documentations, and source code libraries for second-level programs. In Linux, we can traverse the tree using something called the absolute path or the relative path. An example of the absolute path would be trying to access the doc file from our root directory. We would have to type out each subdirectory along the way, followed by a / until we've reached our doc file. An example of the relative path would be if we were in our shared directory. We would have immediate access to the doc file without typing out every directory along the way. Here's some simple code that demonstrates user access. In this example, if the current user tries to change directory into the root directory, the operating system will check the current user's privileges to see if the current user has permission to change directory into the root. In the example, only the superuser has access to the root. If you are logged in as superuser, you have permission to change directory into the root. Otherwise, you will remain at your current directory.